This is the second session of this lecture. So in this part of lecture, I'd like to discuss the measurement of this loop gain. That was explained conceptually in the previous session, but hardware measurement is something like this. Okay, there is a one-to-one, is practical transformer, and I added this. This is required. I'll explain that later. And this VT is not 0. It's something similar to the 1. Okay, 1 or less, something like that. It depends on situation, but this value of this is typically 0.5 and 1 volt. Okay, so there is a sinusoidal wave, and this frequency is sweep. We sweep. Okay, we inject one frequency at low frequency and another frequency at higher frequency. So this frequency of this sinusoid is swept. Omega S sweeping. You know what sweep means, okay? Sweep means like this, okay? It covers a range of frequency. For example, from the 10 Hertz to 100 kilohertz continuously, okay? So this one is this, okay? So this noise will be any frequency with some magnitude, okay? So this is injected into this circuit, all right? And this is the ideal. This is the practical transformer. So the equivalent circuit of this part. So this part is conceptual one, okay? Then equivalent circuit is there is this resistor, 47 ohm or smaller than that usually. Okay, so let's use 40 here. Oh, this is okay. Use same one. Okay, and this one is what? This one is RM. RM is very large, maybe infinity, very large. And there is an ideal transformer. Okay, this is 1-to-1. And there is a resistor, and this is a sinusoidal waveform. This is a VT. This is a 47 ohm. And this is connected to the output, and this is connected to this part. So let me label this as A here and B here. Then this is A and this is B. Okay, understand this? Okay, this is the equivalent circuit. First, this is necessary to protect this signal generator. Somehow this is shielded. By shielding this, the equipment will be damaged. So this is necessary for the protection. You are very careful. Maybe you don't need this, okay? But this is good to have to protect your signal generator or the output port of impedance analyzer. And this is the 1-to-1 transformer. And you gotta use big transformer with large window area to increase RM. Okay, so you need like PQ 50-50 is the largest one, and maybe 100 times like that. Okay, that's the extreme example, but increase this and this. All right, if there is no path here, then this will be saturated eventually, because there are some DC component in this current or voltage, and this current DC voltage is applied across this, then eventually this will be saturated. To avoid that, you need alternate paths for the DC or low frequency component of this current. So the most of the current of this will be passed to this, right? And this voltage Vx will appear here because this is 1-to-1 transformer. So this Vt, this voltage is Vt. Okay, so define this way. Maybe this polarity is opposite. We define Vt plus minus. Okay? Then this voltage is Vx, reference to the ground. This is the minus Vy, reference to ground. Then Vt is actually here, Vt is sum of two signal. Okay? Maybe Vt, magnitude of Vt is 1. Then 1 will be divided to here, according to the characteristic of this loop gain. Okay? Understand this? Right? Because this is equal sum. Equal sum, the ratio of two AC signals with a constant sum. Constant sum is Vt. Vt hat. And two AC signal is Vy hat and Vx hat. Okay, understand this. All right. So then, same as the previous case, this will go through this, and there is some sinusoidal component, and will pass through this. Okay, because of negative sign, to have positive quantity, the Vy is defined as minus Vo. So Vy will be this, and Vy is this one. So it's not the same as this because we have the voltage in between. So this is the equation. Previously, Vy was same as Vx. That is not true anymore. And we have this. So this is sum of this and this injection signal will be divided into two components. One is Vx and one is Va. Sum of them are constant. If they are equally divided, then the loop gain becomes what? 1. Right? If loop gain at that frequency, that is the loop gain crossover frequency, at that frequency, magnitude of Vx and Vy gotta be same. Okay? That is the definition of loop gain frequency. If loop gain is very large at low frequencies, this is very small. Vx is very small and Vy will be very large because of large gain, loop gain at low frequency. At high frequencies, loop gain is very small. Then that means this one is very large and this one is very small. Okay? So this is understanding this is very important. So they are dividing one constant sinusoidal injection signal into two discrete value, and they are different. So based on this equation, they are separated. And then if you measure this with respect to the ground, and you calculate the ratio of them, you measure what? Loop gain in operational condition. Converter is still operating because DC is passing through this, and you are injecting the only AC in the middle of DC pass. You are adding these things, superimposing on this using this insertion circuit. Okay, and with this you may get this. Okay, this is this one, and this is minus because polarity is opposite here. Minus here. This one is what? This is a loop gain, but this is not actual one because you have something here. This will affect this value, but the error is very small. You can make the error between this one is a pseudo loop gain. This is, they pronounce it as pseudo. I don't know why pseudo. Pseudo loop gain is similar, very similar to the true loop gain, and this is measurable. Okay, so this can be applied all the system. Okay, feedback system. This can be applied even there is no explicit feedback path. Okay, it's very general things. And Dr. Middlebrook, he proposed this long time ago. He made many contributions. Okay, and this is one of them. Right. So this is very profound contribution, not only for power electronics, for all the circuit electronics and feedback amplifier. Okay. Before this, they don't know how to measure the loop gain in operational condition of the system, which can be considered very, very tremendous job, okay, very, very difficult job, but he proposed this in his paper. In his original paper is very thick, and he considered everything. So this is just the essence of his claim. So people adopt this to measure this. Okay. When I was studying this, I just wondered why this without this. Okay, they didn't specify this. Why this should be the loop gain? Very strange. Okay, but the trick is here. So this is a very profound fact here. Okay, so transfer function between this, we are using TMS, and we call it as a loop gain, and we don't distinguish between true loop gain and pseudo loop gain anymore. Just take the loop gain because the theoretical background is very different. The numerical value with some condition is very similar, so we don't have to distinguish between them. Okay, so this is the experimental measurement of this. Okay, similar thing can be done in the software empirical method. Okay, empirical method is very similar to this, but empirical method is providing true loop gain because numerically we can add whatever we want. Okay, so it's just program. It's not hardware. Okay, there is no KCL, KVL in there, just numbers and the equations. So we can do whatever we want to do. Okay, so computational simulation will generate true loop gain. The consensual loop gain we discussed previously, but this measurement technique only provides something very similar to the true loop gain. We call it pseudo loop gain, but we don't distinguish between true loop gain, pseudo loop gain, and call them loop gain, and we use notation TMS. Okay, so this TMS. This is the empirical work, experimental measurement, or computational simulation. I'll discuss this in the next lecture. And these two are empirical method, and there is analytical method. If we know the small signal model of everything, you can derive by them by multiplying the gain blocks together. We know the gain blocks between duty ratio and our voltage. We know the transfer function of this one, voltage feedback compensation. If we know the modulator gain, small signal gain, we multiply them together and put minus sign in front of the result. Then is the analytical analysis. This is same as true loop gain, conceptual loop gain. Okay, this is true loop gain. Only this one is a pseudo loop gain. Okay, but this one is measurable. Right? Okay, so now it becomes very smoothly. Assume you understand most of this thing, and this is not 0. This is 0.1 between 1, something like this. I'll explain this later, which number you use, and maybe you select some discrete point. Okay, if you don't have that equipment, impedance analyzer, you do this and use this signal generator, sine wave generator, and you manually change the frequency and measure this one with the scope, and you estimate the magnitude of this, then you plot this, and you measure the phase in between, then you plot this. Okay, that is the way of doing this in the past. Okay. In the 1970 or 80, most people use this, and everything is coming in as one equipment, impedance analyzer, with many other things, many fancy stuff, digital stuff. Okay, okay. So loop gain measure and the sinusoidal response of the loop gain at omega d, what one particular frequency, magnitude response is relationship between magnitude of the sinusoidal component, phase is phase difference between this and this, and you plot this dot, and at this particular frequency, this is magnitude response, and the phase becomes this one. This converter is stable or unstable. This converter is unstable because at this frequency, this magnitude Tm is larger than 0 dB. That means that is larger than 1 is unstable. If it occurs here, this angle is marginally stable. If it occurs here, this angle, then it's stable. Okay? So this is concept of frequency response of this converter. So we are increasing the data point, and maybe we sufficiently decrease the distance between data point, then the continuous curve will be obtained. This is magnitude response curve, and this is phase response curve. Okay, and this is the diagram explaining the measurement of the loop gain. So this thing is part of impedance analyzer, and the impedance analyzer is catching this and removing this ripple component and this DC component numerically, and it processes this and generate this ratio of magnitude and phase delay. So this is the screenshot of that equipment. There is some noise at at low frequencies. Okay, that I'll explain the reason for that. This region is very susceptible to this noise, and this high frequency region is also susceptible to the noise. Inherently, I'll explain the reason for that and the technique to avoid that. Okay. Anyway, this is the result, and this is the equipment setup. Okay. This slide can move very fast. Okay, I can go fast. This is just illustration, pictorial things. Just to take a look at this. And this is the setup. Okay, this is the setup. This was a flyback converter, or flying flyback converter. Okay, and I magnified. This is impedance analyzer, and this is a transformer. I explained. It's built on this PQ 5050 core, which is this size. Okay, there is one guy, very diligent guy, and he wrapped maybe 1,000 times. Okay, and we obtained this. Okay, so this one was good, and I used this resistor, and somewhere this resistor to protect this equipment, and this is okay. Now this is plus minus, this is minus plus. Okay, so maybe you need to use differential probe here, but performance of differential probe is inferior, usually inferior to the regular probe. So you can use regular probe, then you need to adjust additional phase delay of 180 degree because of sign change of your measurement. Okay, right. With that, okay, but using high performance differential probe is okay. This is very good. Okay, for the high voltage output applications, this can be very high voltage. 400 volt. If you connect directly, then this guy will be dead. Okay, this part will be get fired. Okay, to avoid that, you need use the attenuated probe, something like that. The performance is worse than regular one. Okay, if you add something in it, it becomes worse and worse. That is the law of the nature. Okay, but this is measurement. This is the result. Okay, finally, I'll show the video of measuring this. Okay, let me go to Google Drive. It's coming up, right? Okay, so this is the equipment I was talking about, and this is the picture of the measurement setup. So you see this, and this. This is a transformer, and maybe this is the DC passing resistor, and he's monitoring the inductor current using current probe, and now he's connecting the sinusoidal waveform. This is coming from this transformer, isolation transformer. This is a simple transformer. By the way, somehow they make very small using high mu magnetics, and they sell it for $200, something like that. Okay, they are stealing your money. Is connecting to the output to sweep the sinusoidal wave frequency, and this is connecting to, this is Vx probably, I don't know. One is Vx, one is Vy. With respect to the common ground was somewhere here. Huh? This is for simply the inductor current monitoring. Okay, it's nothing to do with the measurement of this. Okay, I think we are ready. Not ready. This was the general purpose flyback converter. I mean, what I mean generally is I can disconnect with some jumper line, so you can measure everything here using just one hardware. You can measure control to output, duration to output, input to output, so on. Okay, it's measuring, and this showing this. Okay, this is loop gain, and this is a noise. Okay, just think this is smoothly connected. Okay, there is a reason for this. At low frequencies, it goes relatively slowly. Because at low frequency sinusoid, you need to take many points to calculate something. At higher frequencies, you need to select the smaller, fewer samples. So this low frequency is moving slowly. This one is very funny. Okay. All right, it's almost done. I think this is 0 dB line. It's moving, and it's done. Okay, and this is a comparison with measurement. This is a theoretical curve. This red one is generated the computational method. The other one is measured one. Okay, so it's end of this show. And let me take 2 minutes of your time. Close the performance. All right, so I made note something here. Somewhere here. Okay, let's take a look at this. Minus 180 degree line is. This is 180. Okay, let me use that one. Minus 180 degree. Okay. And at that frequency, magnitude is. Oh, okay. At that frequency, this frequency. Magnitude is this one, okay? So because this is below this 0 dB line, so it's smaller than 1, so converter is stable, okay? If we increase the magnitude only up to this point, here, it becomes marginally stable. So this is called gain margin. We'll discuss the gain margin and phase margin formally in the later time. But this is gain margin. Gain can be increased this much while remaining in the stable state. Okay, and at this frequency, 0 dB frequency, phase is this much, okay? Phase is this much, but somehow phase is changed like this. It goes something like this. Then it becomes at this line, and it becomes 0. It becomes minus 180 at this point, and it becomes 0 dB. Then system becomes marginally stable. Then you have this much of margin. Okay, so this is gain margin. No, phase margin. So we have, in terms of phase, we have this margin. This is PM, phase margin, and gain margin. Okay, so from here, this is obvious. This becomes phase margin. This becomes gain margin, and this noise is generated by something. Okay, because the reason for that is this is always true. Okay, this sum is constant. For some case, one of these can be very small. Okay, smaller than some noise level, then it causes some problem. So that is the why we are seeing this noise problem at low and high frequencies. Okay. Okay, so that's it for today. All right. Okay, thank you. Thank you for your attention.